In this video, we'll be looking at some of the formulas we use to make it a little bit faster to take a derivative. This is going to be a very proof-heavy video, so there aren't any exercises aside from one partial exercise towards the end. You'll know it when you get to it. We have arrived at the part of calculus that most students love and some teachers hate. The part where we teach you how it's possible to take certain derivatives a lot faster without having to use the definition of a derivative. Now, I do want to warn you that with these shortcuts, you do not want to just stop using the definition of a derivative or forget how to take the definition of a derivative, because they don't always work with every single kind of function, and there are going to be some questions where you need to utilize that definition of a derivative, such as when we were looking at the absolute value and you had to demonstrate that you could not differentiate it at a certain point. You had to prove it, not just say, oh, well, because there was a corner. Okay? Now, a part that got left out in the words up here because of space was that when we are utilizing these rules, when we're saying let f and g be functions, we specifically mean functions that are differentiable at x. Okay? Because obviously, if they're not differentiable at x, we can't take the derivative. It seems like a gimme, but it's important to make sure that it's said. Okay? And then, of course, c is just going to be a real constant. Now, I've put them here because I'm not going to bury the lead on you. In a typical class, you would prove these, and then you would get the nice list that you would then get to use. Obviously, because this is a video, you can just come back and see it, and I know that this is the thing that you want. So what we're going to do is we're going to go over these, and then we're going to prove each one works. So let's go ahead and state them, and then we'll get to the proofs. So on this first one, we have that the derivative of some constant is equal to 0. That should make obvious sense because a constant is a flat line. The slope of any flat line is 0, and a derivative is a slope. Similarly, the derivative of x, meaning that we have a line 45 degrees. What's the slope of any 45-degree line? That's 1. So the derivative of x is equal to 1. From this, we get to what we call the power rule. This is that the derivative of x to any power is going to be equal to n, meaning that power, times x, and then we just take the power minus 1. So for example, if we had x to the third, we would say, the derivative is 3x squared. You'll see examples of that when we prove it. Over here we have some constant times a function of x, and we take the derivative, so the derivative of cf would be equal to, we take out that constant times the derivative. This is just like the limit rule, where we took the limit and we could pull out that constant, because remember, a derivative is a limit. So for example, we had the 4.9 and we pulled that out of the limit before we took the limit. We're doing the same thing here. We just can take that constant out. Okay? Here we have our sum rule. Works just like it did with functions, just like it did with limits, which is the derivative of the sum is equal to the sum of the derivatives. Here we have our difference rule, just like our sum rule. The derivative of the difference is the difference of the derivatives. Now, the power rule and the quotient rule are a little bit like the quadratic formula when you're working in algebra. This is where students start to try to learn mnemonics and rhymes, because the order of where you put these things does matter, especially in the quotient rule. So do pay attention. Also, you'll notice that I've been switching back and forth between Leibniz and Lagrange notation. That's because it is important that you also make sure that you are comfortable using both, especially if you're going to be taking any of the standardized tests, because you don't know which version of the notation they're going to use, and you don't want that to trip you up. Okay, so over here what we have is the product rule, meaning if we have two functions that are multiplied together, or a function that we can decompose into a product of two functions. If we take the derivative of a product of functions, then we can take the first function times the derivative of the second, plus the derivative of the first function times the second function. And again, we're going to prove this. And then for the quotient rule, using our normal, of course, rule that g has to not be 0, we would say that the derivative of the quotient is equal to the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator divided by the denominator squared. And again, we'll prove that also. So let's go ahead and prove these first three now. For all of these situations, we're going to be using the exact same criteria. We're going to have f and g be differentiable functions on some x or some interval of x, and then c is going to be some real constant. So the first example, we have f of x is equal to c, a real constant, and we're going to be taking the derivative of the function on x. But it's not going to matter because when we take the limit as h approaches 0 of the f of x, well, f of x is just c. So when we go to plug in x plus h, that doesn't matter because it's always c. So we simply get c minus c, and c minus c is 0. So before we take the limit, because we know that the h is never going to be 0 because we're taking a limit, we divide it out, we get 0, and the limit as h approaches 0 of 0 is just 0. So there we go. We've proven that no matter what value we pick for c, our derivative is 0, which perfectly lines up with our understanding of slope. Similarly, if we take f of x is equal to x, we're saying that that's our line where our slope is 1. So we take the derivative of f of x, we take the limit as h approaches 0, we plug in x plus h minus x, and we've done this one. So the positive x and the minus x are going to cancel out. We get h divided by h, which if we were not taking the limit would be impossible, but because we're taking the limit, we're allowed to divide. So before we take the limit, we divide out the 1, we take the limit as h approaches 0 of 1, and it's simply 1. Now, the third one might look like a big block of gobbledygook, but if you remember your algebra, specifically your algebra 2, hopefully you remember binomial theorem. If you don't remember binomial theorem, you can possibly do the expansion or utilize some other methods of proving this one. I happen to like binomial theorem because I enjoy combinatorics. So I'll walk you through this one. Again, we're simply going to take our function and it's going to be x to some power. This is our power rule, okay? So we take the derivative of f of x, and so we're going to replace the x with our x plus h, and then we have our x to our power. Now, anytime we have a sum or a difference, we can simply use binomial theorem. And the only difference in binomial theorem with a sum and a difference is whether or not we have an alternating sign term. And because this is a sum, we don't have to worry about alternating signs. So with binomial theorem, you can use binomial expansion, and if you remember combinatorics, you can simply use a combination. If you don't, you can draw out Pascal's triangle, that would work as well, or you can, I guess, brute force the method, that would also work. Because in the end, all we really care about are going to be the first two terms of this polynomial, as you'll see when we work through this. So this is binomial expansion in summation notation over h. This is exactly equal to this, okay? So we've expanded it here, and over here, just as a reminder, I've written out exactly what the combination looks like. So this is simply saying that the combination of n choose k is n factorial over k factorial times n minus k factorial. What's important about that is that tells us that we're going to have an n in all of these things. But more specifically, that tells us that c of n choose 0 is 1, and c of n choose 1 is n. Go ahead and work it out for yourself if you need to. Now, when we work this out, we have our x to the n over here, and we have our x to the n over here. They're going to cancel out and drop away, leaving us with an nx to the n minus 1 times h as our first term. And then you'll notice that every single term within here happens to have an h. So we divide out the h in the denominator, leaving every single term except for the first term with an h. So at that point, we have a sum of terms in a polynomial where every single term, except the first one, has an h. So if we take the limit, that's just the limit of each of those terms individually, which means all of those terms, except that first term, go to 0. So we're left with just that first term, meaning that, hey, that big complicated mess just becomes n to the x of the n minus 1. So no matter what our power is, if we have x to some power, it reduces to this. Pretty good. Next we have the sum rule, and you'll notice that I skipped the coefficient rule because based on what we did, I'm leaving that for you to prove. Just like, based on this one, I'm going to leave the difference rule for you to prove. So walking you through this one, I think that you'll be able to do the difference rule pretty easily. What we do here is our old friend, the change of variables. So in order to prove this one, we don't just go directly in. We actually start by saying, hey, let's go ahead and work with what we do know, which is how to just use any old individual derivative. So we're going to set up some function and say it is the sum of these two functions that we know are differentiable. So then we're going to take the derivative of that function. So we take the derivative of this function, and it looks like this. And so because we're taking the derivative of this function and it looks like this, well, we know that this can be replaced with that. So we're going to go ahead and do that. We're going to take the limit of this guy, and we're going to simply replace it. And then we're going to work through our algebra chain. Now, when we do the subtraction here, we're going to maneuver things around. So we get our f of x plus h minus f of x, g of x plus h minus g of x over h. And then we're going to split it up into the two fractions, use our limit properties. Remember, I mentioned earlier that those would be important, so that we can split that limit across that sum. And now we've got the limit over here and the limit over here. But by definition, this is simply the derivative of f. Hey, we said it's differentiable. We can do that. And this is simply the derivative of g. We can do that. And then this is the derivative of r, which is the derivative of the sum of these two functions. So we've taken the derivative of this sum of functions and shown that it's equal to the sum of the derivative of those two functions. For the proof of the product rule, we're going to do things very similar to how we did the sum rule. We're going to start with a function that's equal to the product of two differentiable functions. And then, of course, we're going to take the derivative of that function. That's our limit as h approaches 0. And then we're simply going to plug in our original functions. Now, this causes us a bit of a problem. And one of the things that we have to be careful of here is that we look at these proofs from a modern standpoint, where they've already been completed and we actually already know the result. But when you approach these kinds of problems in the field, or when you approach these kinds of problems even on like a homework assignment with functions that you've never worked with before, you're not going to necessarily know what the end result's going to be. So when you're approaching problems like this, it's best if you approach them from the standpoint of what is the strategy that you should be engaging in. And so when you approach problems like this and you're trying to figure out how can you solve it, how can we deal with this, what algebraic or calculus strategies can I try to employ, what you should be thinking of is, what is causing me a problem? And in this situation, the thing that's causing us a problem is this h right here. Because if this wasn't here, we could easily take that limit and we would get f of x, g of x minus f of x, g of x. That would be 0, but we could take that limit. That h, though, means that we can't take that limit because this becomes undefined. So we need to find some way to manipulate or move this around in order to deal with that. And in previous ways, we've done this by dividing the h out, or by making it so that we had another term down here that would be adding or subtracting to the h, or moving the h into the top, doing something to the function that would cause us to not have a problem. Another option is if we can redefine or move things around in such a way that this h ends up looking like the definition of a derivative. Because then at that point we can just go, oh, that h isn't actually being a problem because it's just going to get slurped up into that derivative, and then we've just taken the derivative of a function. Which, again, because of our modern brain, we know that that's what happens here. But even without that, we know that if we could take this f of x and somehow get a minus f of x with it, with this h, because, you know, there is a subtraction here, we could break a fraction up, that would solve our problem. So if we could introduce a term to do that, then we'd be good to go. And this isn't the first time we've used that kind of a strategy. That's actually a common strategy for solving polynomials. If you remember, before the quadratic equation existed, this was how we solved polynomials with completing the square. So we're going to use that same strategy. We're going to take a plus and a minus of a term that's going to let us factor things out. And again, the thing that makes me think, hey, let's factor, or I should say not me, once again, modern brain, I know what the result is, but the people that originally would have developed a proof like this, the thing that makes you think factor is, I've got a product. Anytime I'm working with a product or a quotient, factoring should always be on the table for you, right? So we introduce a new term that is something where if I can factor out an f of x, I've got a g of x and a g of x plus h. And then if I factor out a g of x, I've got an f of x plus h and an f of x. So the term I introduce is f of x plus h times g of x. That deals with this term and deals with this term. And I'm never allowed to just put something into an equation or take something away. It always has to be equal. So I add it and subtract it. It's kind of like Indiana Jones. I want to take something, I gotta swap it, right? So I add and subtract at the same time and hope there's no giant boulder around. We do that, and then because this is in fact a fraction, we break it up. So now I've got an h in both places. So now I'm going to get a derivative in two places. Then I factor out the part that keeps me from having a derivative. Over here it's the f of x plus h. Over here it's the g of x. Now when I take the limit over here, x plus h, this is differentiable. We said it is, which means it's continuous, so I can take that limit. That's no problem. And then over here, well, that doesn't even have an h, so taking the limit here doesn't matter. And then that's a derivative, that's a derivative. So therefore, this derivative is equal to f of x times this derivative plus this derivative times g of x. And that's our product rule. Now with the quotient rule, we're going to do things exactly the way we started out the other ones. We're going to start with a function that's going to be equal to the quotient of two differentiable functions. Now, unlike the other versions, it is going to be very important that our functions are differentiable here. It was important previously, but we didn't directly address it anywhere other than saying, hey, they're differentiable, we can take the derivative. Here, there's an additional reason it's important. Now, we go ahead and take the derivative, we plug in our values. At this point, we have fractions. And this is where it being differentiable matters, because the fact that they're differentiable means that they're also continuous. That's going to come up right here towards the end. So we find our common denominators and we reduce to this fraction. This is the point where we get our g squared, because if we could deal with this h right here, when we take the limit as h approaches 0, it doesn't change this g, and this g is, oh, that h is going to go away, so we get g of x and g of x. Well, that's g of x squared. So that's where our g of x squared term comes from, right here. And then this term is the one that we've got to deal with that h. And you'll notice this big block of text right here. And this is the mean calculus teacher and me coming out going, hey, you know, this looks a whole lot like that product proof we just did together. And in fact, you can work this out using almost the exact same technique with a slight difference that you as calculus students should be able to figure out. And I think there's a lot of value in you being able to figure that out. So I'm going to leave this one for you to do, and in fact that's going to be the exercise for this video. And unlike the other ones, I'm not going to put the answer at the end of the video because I think there's a lot of value in you trying to go ahead and work it out. Now, if you get to the end and you aren't able to do it and you just become really frustrated with it, please do go down to the comments and just ask for it, or jump into the Discord. I'll go ahead and post the proof for it there if you ask for it. Not a problem. I'm not that mean, okay? So I hope that introduction to the derivative rules helped you out. And when you finish up that quotient rule proof, please do share your work either in the comments or on the Discord.